Up next, main event. We have software engineer from LSST Telescope, formerly,
yes,
and also TI-84 programming cheat code extraordinaire. Christopher Contaxis.
So I'm going to go over about me. I'm going to find out a little bit what everyone here is kind of interested, so I can at least cover a little bit of the various topics. And then the rest of my presentation here is just pictures. I'd rather just talk to the pictures as we go through. So I've been interested in software since roughly 10 years old. When I got a TI-86 plus calculator, and I determined I could use that to cheat in math by programming all my equations into it. And that's how I started programming. I've been in working with software in optical and hardware control applications now for 10 years. My interest in astronomy is largely due to the engineering involved, instrumentation, and the mechanics and making the machine itself work, rather than as much about the science. And I've been doing my own astrophotography for roughly 5 years, however, much more rarely than I would like to. I'd like to know just generally if someone, how many people know a little bit about LSST? Or read a little bit about it, watched, there's a couple of TED Talks about it and all that stuff. What about large observatories in general?
Seen a few.
Yeah. I know like, you can go to a bunch of places in Arizona, visit observatories, all that stuff. And then how many people have some knowledge of like control systems and the types of things that go on behind the scenes in large observatories for optical purposes and whatnot?
A little bit.
Sort of.
Okay.
Kind of.
Enough.
So generally just 1 or 2, 3, 4 people, however many, just what would you like to see covered?
Covered the telescope.
Yeah, the LSST. They changed the name.
Yes, they have, but I'm so used to LSST I can't remember what's it now.
I'll Google it.
So, okay, I'll get over this, but first I'm going to talk about just LSST in general. It's a surveying telescope with the goal of
Interferometry.
yes,
That's right, yeah.
with the goal of imaging the entire southern hemisphere night sky every week. It's going to do that for a minimum of 10 years. And the idea is that over that 10 years, you get a massive, basically, movie of the entire southern hemisphere night sky. What that means is you get to see a whole lot more of what's actually going on behind the scenes rather than these little small images of one small portion of the sky taken from really small field of view telescopes looking for, exoplanets or some really tight detail on a specific set of stars. This is looking at field of view of roughly 3.5 by 3.5 degrees per image. If you have a couple $1 billion, yeah. I mean, the camera for the LSST is 3.2 gigapixels. So you're going to need gigabytes of space for a single image. It's going to take one image every 15 seconds, and it's going to do that all night long. So the time between moving from one shot to the next shot for different visits is roughly 3 seconds for a 9-degree slew. So if you have this massive telescope moving 9 degrees in 3 seconds, that's a lot of power very, very quick compared to other observatories.
How many filters does it have?
It has 6 filters, but the filter wheel only supports 5. So they will, during the day, switch out a filter to get to utilize that filter. They want to try to cover the whole night sky with every single filter within every week. Whether they can actually do that is still something I have to figure out.
That was a fairly big filter too.
Oh yeah, I mean the camera itself, the sensor area, I think it's like around this high. off the ground. It's a total of 100. This is off the top of my head. I think it's 178 or 187 4K by 4K CCDs. It's a big, very, very big
Let's see where the billion comes from.
sensor.
Are they standard sensors? Like you find
No,
on camera?
they're custom.
Okay.
They can be manufactured. There's 2 manufacturers. The interesting part from a science perspective is that each image is supposed to be processed within 1 minute of it being taken. So the idea is that you run through a whole set of different science proposals on that image. So you might be looking for things like, did a star go supernova? And then within that minute of processing that image, you would get a stream of events saying, at this star, we believe is supernova, this, you have a whole list now of all these different events that they have seen within that image, that then any other telescope that connects to that data stream can say, I'm going to automatically slew my telescope to that star. So where LSST comes in is it does see very deep. I mean, it goes to 26, 27 magnitude stars in a 3.5 degree by 3.5 degree picture. So it sees very, very deep. But it's not cut out for the types of sciences that you would want to get to, like really observe like a supernova or something like that. I'll get to you. So the idea is that you get that information from that image and you try to slew other telescopes that are actually good at collecting more detailed information to that as quickly as you can, so you don't lose it. You don't want to take a bunch of images, process it 10 days later, and find out 10 days ago something interesting happened, and it doesn't really help you. Right?
So LSST's job really is just it's sort of to give people the heads up that there is something interesting to come do science on.
Yeah, and
It's not really, it's basically more like it's just a generator for other projects and studies to go and be done. It doesn't necessarily do much itself besides send out tons of alerts constantly.
Well, it also
all the times.
is used for mapping out dark energy and how it changes over time. So it would automatically do things like tracking gravitational lensing that's occurring and see how that lensing changes over time to see how you can figure out what's going on at a larger picture scale of the universe. It also does things like looking for new bodies within our solar system, because it's constantly taking that southern hemisphere. So it's very helpful when you're just watching everything every single week to get an idea of what is going on everywhere. So the joke is, if the first one works well, there's going to be one in the northern hemisphere within a decade. So yes.
45 range.
It's
Well, maybe not get it from
UVR
the filters, but
UVRGBI.
okay, so
Yeah.
IRR of UV, I would think.
Yeah.
Plus,
Well,
The usual.
not IR.
no.
oh, probably near IR.
Well,
So what
I can't
what's
remember.
detector type? Are we? Do you know? Is it-
No. That was outside of what I
It's
did
okay.
particularly. So, my role before I left earlier this year and like mid last year was the primary mirror system. So I wrote the control software to do everything with the primary tertiary mirror. It's a very unique mirror in that it was the primary and tertiary mirror in a single piece of glass. So what does that actually look like? It looks kind of like, it starts out like this, with people placing a bunch of cores into a giant furnace where they're going to melt down a bunch of glass and cast the mirror. So what you see here is where they're blocking out the different cores in the honeycomb structure of the mirror. This is them loading up a whole bunch of glass. That's a lot of glass. And what they do is they melt that, they keep it spinning nonstop, and they very, very slowly cool it down to while it's always spinning. And eventually you end up with that. A giant block of glass that has to be figured.
That's very lightweight, isn't it, relatively speaking?
It's 17 tons.
Yeah, it should be a lot more than that.
Yeah, but then also thermally you couldn't do it because it's borosilicate.
Never cooled down.
Borosilicate is it's a lot cheaper to make than something like a ULE, but I would argue that you end up spending that money in your support system and thermal system to try to keep that glass temperature as close to ambient air temperature as you possibly can get. So there are trade-offs there. And this is what it looks like polishing. You get to walk on the mirror. As strange as that sounds. Yeah.
He does a shuffle on it.
Yeah.
How does walking on the mirror not screw with the polish or give it micro scratches? Does it not matter on that scale?
It doesn't matter at that scale. I mean, you're talking, you have 8.4 meter surface. If you're talking about one small little error in the surface, it's not going to attribute to that.
If you have people walking around it for
They don't, well, to be fair though, they're not walking on it like with day shoes or just any old stuff. It's very specific footwear. And then here you can actually, it doesn't really come out well here, but you can see here's the surface of the primary mirror here. And then here you get a very big change in the surface here to the tertiary. So,
That's pretty neat.
so what does it look like when you start integrating? It looks like this. This is a surrogate mirror here made out of steel. The manufacturer of this got very, very close to the actual weight of the mirror. They were only something like 600 pounds off, which was pretty incredible. And this is how we tested everything first. You don't want to put your one-of-a-kind 8 years to make mirror and then start testing your hardware and software and then accidentally break that mirror. So you put a metal one that you can't break. And how everything happens is you have, for this type of mirror, you have two different support systems to support the mirror. The first is a static support where power goes out, it's going to hold the mirror in place. The mirror is not going to, flop off. And it has to be able to support it at all elevation angles. So you could be horizon pointing and power shuts down. The mirror will fall a little bit, but it will be caught by, there's many of these guys, static supports here that will then support the mirror and keep it in place. You can't do any observing or anything like that on static supports, but that's where it would be. Like the idea is if there's an earthquake, there's a lot of earthquakes in Chile, you would lower it to the static supports as quickly as you can get it, and then the static supports would keep it safe as to whatever it's designed for. So what you're seeing here is the this right here is a collar, a little thing here that goes in and holds the mirror to this, basically you could think of it kind of like just a giant spring. And they're everywhere. There's over 400 of those throughout this whole system. Each one tested to find out the characteristics of that specific unit and then put in a spot within the mirror where it best serves its purpose there. So you might have stiffer ones towards the outside where the mirror, when I say the outside of the mirror is about yay high on me. And when you go all the way to the center where the tertiary mirror is, it's about here. So that's the change in thickness from the edge of the mirror to the center of the mirror. Yeah. Yep.
Is the mirror lifted off of those
Yes.
contraptions when it's actually going to be used?
Yep. And I have movies of that happen. That comes later. And then what you're seeing here is you have two different types of actuators that are responsible for, one set is responsible for lifting the mirror. So they handle lifting that 18-ton mirror up. But they have no stiffness. So if you just lift it up and you have nothing to define the position of the mirror, the mirror is just going to go all over the place. It's essentially floating, so you could kind of also think of it like air hockey. If it was perfectly stable and it was lifted with those, you could take your finger and just kind of poke it like an air hockey puck, and the mirror would move. You can move it wherever because its weight is fully supported by those actuators. The other set of actuators, there's 6 of those, is the hardpoints, and they define the position of the mirror relative to the cell. So right here is the cell. This white stuff, everything below is the cell, and it has everything needed to lift, support, and figure the mirror to a specific shape. And what you're seeing here is a support actuator connecting to a load spreader. And what a load spreader does, it just takes the single point that the actuator connects to and spreads that force across, in this case, 3 different points on the mirror. So you're lifting it and, yes?
What is the diameter and the thickness of that mirror?
The diameter is 8.4 meters across.
Wow.
I don't know the exact number for the thickness, but on the edge, it's about up to here on me.
Wow.
And at the center, it's maybe like 8 to 10 inches, something like that. It's a very wide range.
You said it changes shape?
Yes, but when I say change shape, I mean we're talking a very small amount, like 100 of nanometers in terms of figure. It's not like you would ever see any difference with your naked eye. And this is what it looks like from the outside. Over here you have 2 support actuators out for testing before they get put into the cell. And this is what you would walk into to get into the cell, get in there, maybe install an actuator, figure out why an air hose, because these actuators here are pneumatic. So you have a giant air tank right here where all the air is just temporarily held. You have to constantly feed air in with a compressor. And that air is then distributed to there's a total of 156 of these actuators in there. You have to constantly feed air in so that you can keep that force on the back side of the mirror to get it up off the static supports. And when you first put this type of system together, you're going to turn on air, and the first thing you hear is a bunch of the hoses have gone flying out because you didn't connect them all the way, or maybe one of the joints was faulty and you have to replace it. So you have a lot of fun during that stage. Here we have a very high-tech solution for testing some of the systems in here. It's called just a little bag weight. It may not look like much, but with a couple of those you can do quite a bit in terms of figuring out how much force is placed on the mirror that you don't expect. And an unexpected load within like the context of an observatory might be wind, right? You think about wind and you think about, well, 2-mile-an-hour wind, that's not a lot. But when you have an 8.4 meter mirror and you have a 2-mile-an-hour wind pressing on it, with that much surface area, it will do a lot to really
move it.
Not move it, but impact your image quality negatively. So, and then the control side of things. Here's just some of the cables that we hook up. So here's the control cabinet here. This is eventually going to actually be mounted to the side of the cell here. And then as part of testing, we had to run a long set of cables to the bulkhead here. But within the actual telescope thing, the cables would only run from here to here. So they'd be a lot shorter. But there's a lot of cables involved. And that's what the control cabinet looks like for the mirror system itself. You got everything from power supplies here to an interlock system for like hardware safety and personnel safety, to the control computers right here, and then you have also a bunch of relays and a bunch of other just wiring things. Other things that are not pictured here is you actually would have coolant lines rolling in here, and you have a heat exchanger here. So you pull out all the heat that this produces. It produces a ton of heat when it's running. You pull out all the heat through the heat exchanger and pipe it as far away from your telescope as you can, because heat next to a telescope is not good at all.
Well, you
Especially
said this is gonna go on the
Yeah.
telescope?
yeah. I mean, this weighs quite a bit, but it's nothing compared to like an 18-ton mirror.
So if you've got some kind of a hose that's going from that thing to take the heat away?
Well, you also have it going into the mirror cell, the coolant, because you also have to pull the heat out of what all the electronics that are inside the cell, and then also to cool the mirror. So you have heat exchangers and airflow there to try to cool the mirror itself, keep it as close to the same temperature as the ambient air temperature is. Ideally, if you can't keep it there, you always want the temperature lower, because the impact of a slightly hotter glass compared to ambient is much worse for image quality than if it's slightly cooler. Because if you think about it, slightly hotter, that warmer air is going to go up into the light path and really mess with your image quality. And if it's cooler, it skirts down, so its impact on your light path is much smaller. And part of this testing was also a 15-degree test, where we had a test fixture to lift the entire cell up at a 15-degree angle with the mirror on it, and then we still do all of the same type of testing that we did previously. It is not enjoyable to climb up this ladder with the cables and then get up there to connect it to the bulkhead. It's high. So now we get to the actual mirror. So what you see here, the blue stuff, is a protective coating for when the mirror was in storage. You can also kind of see here the height difference between the outside edge of the mirror and then the inside edge right here. It's a very, very different thickness, which poses quite a bit of problems when you're talking about trying to keep the temperature of the mirror consistent all the way across, right? Because you have a whole lot more mass here than you do here. And so you have to really tailor your thermal system to account for that. And it's not trivial, and it takes a lot of time to get to there. Looking up so this is from inside the cell, I took this picture of the mirror, and it still has the protective coating in this one. But here you can see the honeycomb structure. If you remember from that first picture where they're putting those foam cores in, those end up making these honeycomb shapes here. So what you're seeing here is straight glass all the way through to the surface, while here you're seeing a little bit of glass for the bottom plate, air, and then the front surface of the glass. And this is going directly through to one core. It's really hard to see because my phone camera at the time was really bad. But on each core foam, the Mirror Lab actually puts in a number and an identifier. So each core on the underside of the front surface has an identifier indicating what core it is, and each one is unique. So it's a small little detail that most people will never know, but there is a little piece of glass here that might say like A20 for core A20 or F with 40 or whatever, what have you. And then once the glass was removed, or not the glass, sorry, the protective coating was removed, here's a picture of where the support actuators connect to the underside of the mirror on the load spreader without the actual actuator in place. So it bolts to 4 places here, and then the pneumatic cylinders get connected to this part of the load spreader right here. You can kind of see in this blurry image here, here's one of the low static supports, those spring structures. There's going to be one there, and you can't see it, but there's one right over here too as well. And this is what the mirror looks like under the test tower in now Richard F. Karras mirror at the U of A. You can see here the fiducials that they use for helping identify when they take an interferometer image of the mirror, figuring out where it actually is and what is what. And these are put on by someone who walks. They would just walk on the glass, they go around, and they look at the core to find a specific core, and they try their best to get it in the spot they want it. But it's always fun because if you look at it this way and look at it this way, it looks different. So they just take their time and just go over and slowly through trying to figure it out. And here you can also see the shape difference between the primary mirror here and the tertiary mirror here. You can see that sharp edge, right? It's not sharp, but that clear delineation between the two. Also, you can see here is one of GMT's mirrors. GMT is a multi-segmented mirror, or multi-segmented telescope, where it has 7 segments. Each segment is one 8.4 meter mirror. So when you put them all together, it's close to 28 meter diameter mirror. So it's when you see just one 8.4 meter mirror vertically stood up, it's massive. And then you just take another 2 of those and stack it on top, and it is it's mind-boggling how big they're going. And then you think about things like the 30-meter telescope or EELT, where they're going 30 meters plus.
Insane.
It's crazy. And then for scale, here's also another GMT mirror right here. So you have 2 GMT mirrors here that are in different stages of manufacturing. And then here's me for just scale against the LSST mirror.
Isn't this under the football stadium there too?
It's not under it, it's beside it, but yeah.
Oh, I thought it was under.
No, a lot of people think it's under, and I think a lot of people say it's under because it sounds much more entertaining to say that it's under this football stadium, but it's actually just beside it. This is kind of boring. Okay, so this is what it looks like inside the cell. From the doorway here. As you can see, you can get some nice tables and a wonderful chair, and a lot of head safety hazards everywhere. It's very easy to bump your head in there. Yeah, so you got a lot of different structure in here to all support everything. And one of the reasons why you have all this structure is for mirror coating, the cell itself becomes the part of the vacuum chamber. So they lower the top part of the vacuum chamber over the mirror. It connects to the mirror cell all the way around, creates an airtight seal, and then the mirror cell here is closed up and tightened, so this will actually be under vacuum during mirror coating here. And so you need a lot of this extra structure here for when it's under vacuum to keep it whole. This is what the center of looking out of the mirror cell is. And what you would actually have here is a gyroscope to tell us what is going on with the mirror motion. And then also over here would be a laser tracking system, where when they first raise up the mirror at night, the idea is you use a laser tracker to measure where your primary mirror is, measure where your secondary mirror is, and measure where the camera is. You then tell the secondary mirror and the camera to align itself based off some values to the primary mirror. So that actually gets the whole system aligned every single night, or every time you raise the mirror, and that's where that would be located.
So it's like the world's most expensive laser collimator. Kind of.
Not really for collimation, it's more just positioning of the mirrors and the optics to a reference.
Well,
Just like
basically on center.
Yeah. And this is me. If I stand up in the mirror cell, I have to stand up. This is my eye level, to give you an idea of just what it feels like if you were my height. If
That's
you're
what
taller,
bumps on your forehead.
oh yeah, no, I have cut myself in there. But yeah, so you see there's a lot going on in there, and this does not even have the thermal system in place. So it doesn't have the fan units that are going to be circulating air within there. It doesn't have a lot of other things that go into this. So right now it's actually quite sparse compared to what it will be when it's not fully assembled on the mountain.
You're gonna be able to get into it when it's
Oh, yeah.
fully assembled?
Oh yeah. It just gets tighter and tighter every time you put something else in it. So over here we have a hardpoint actuator. So this is one of the actuators responsible, it's this guy right here, responsible for positioning the mirror. It's got this massive amount of lead counterweight to keep everything balanced, and it's assembled in place. So you don't take the actuator and bring it in, you take the actuator in pieces and then assemble it in place in the mirror cell. Here's another picture where you could see here the counterweight is a little bit back here, but over there is the mirror. So this is a very long actuator. It's about yay tall from the ground. It's big. There's 6 of these in total throughout the mirror. Up here, you can see is one of the load cells that's responsible for determining how much force is being placed on the hardpoint. From a control standpoint, you want 0 force on your hardpoint. You don't want the mirror to be supported by this at all, because that will destroy your image quality. You'll get, from an optical standpoint, you'll get 3 little domes where the hardpoints connect to the mirror, and you won't get a nice clean surface that you're looking for. So there's actually quite a bit going on, and if you remember from one of the first pictures where I had that just bag weight, you use that to test this portion of the control system, because it's essentially the same as if wind is on it. Or one of the things we did was when we had this mirror there, is we would walk on it. We get up on it, walk on it, and the software, based off of the 6 hardpoints and the forces they see, could determine roughly where that person is walking on the mirror based off the forces and moments on the mirror, and then automatically correct that so that the hardpoints see nothing. The support actuators take that load off of the mirror, off of the hardpoints, and then your image quality stays stable.
Is this the steel mirror or is this the real mirror?
This one right here is the steel mirror. Most of the pictures I have are with the surrogate mirror. When we were doing testing with the mirror lab and the actual mirror, we had like 6 weeks total to do everything we needed to do, and that was it. So it was just kind of in that go, finish the job. So here's part of the hardpoint without the lead counterweight and partially assembled. You can see it goes here and it just ends. So it hasn't been fully assembled yet and installed into the mirror cell. And right here, you can see the other end where it connects to, but there's nothing there. And it takes a couple of hours to install one of these. We've talked about those. And this is what a support actuator looks like. There's 2 types of actuators, support actuators, single axis and dual axis. This is a dual axis because you have one going directly into the mirror and one coming in at a 45-degree angle. And that's so that if you think about it, when you're pointing zenith straight up, you only really have to support against gravity in one direction. But as your elevation angle changes, the weight of the mirror is going to change the direction. So you need that, in this case, a 45-degree angle of vector to be able to produce force in that way to support the mirror as it reaches those different angles. So if you're at horizontal, this guy right here is responsible for counteracting gravity completely. And then the axial guys here, the ones that point directly into the mirror, are at that point responsible for counteracting the moment. When you're at a horizontal pointing, right, the top of the mirror is going to want to go this way, the bottom of the mirror is going to want to go this way. So it's going to want to do this. So then you use these actuators, or these cylinders here, up top, use it to pull this way and to push out that way so that it stays in that orientation. It doesn't
Turn into a Pringle.
Yeah. Here is a single axis actuator. As you can see, it's much simpler. It is just one cylinder going up. Nothing too crazy there. And here's just some of the valves that we use. As you can see, this is a single axis actuator here, but there's a whole lot of different hosing going around everywhere to the different valves. Here's a little on-off valve for this actuator. There's a lot that goes on here, and you can see how it would be pretty easy to like connect one hose to the wrong spot, and then you try to do something and it doesn't do what you want it to do.
I'm curious, so why is it pneumatic rather than hydraulic? Is it because you have to worry about the hydraulic fluid doing something?
Well, hydraulic, when you get a leak, do you want that all over your electronics and your mirror and your mount? Air leaks, well, it's just gonna okay.
So it's just, hydraulics are not reliable enough with these kinds of conditions.
Do you want to break fluid on your telescope?
No.
No.
And this is what actually the control electronics looks like. It's a nice green box. And what they did with LSST was it is a lot of the control electronics throughout LSST use the same card here, and then they have a second card on top that's unique for its purpose. And then the box color indicated what its intended use case was for. So, in this case, green was for pneumatic actuators. There's more of those. And now what you got here is here's your main air line going through the mirror cell, where your actuators would connect up to and get their sourced air from. Over here is your main coolant line, where it's going to provide your coolant to the fans, which are not installed at this point. And it will provide your coolant in, and there's a second return line that you can't really see back here, where the return from the fan would come out and get circulated back through the system. So right here, actually I think there's a better picture. There you go. Right here, we have, this is where a fan would connect. Some of them are going to be right up here, and some of them would be located further down. It just depends on however they can fit it into place. And then over here, these guys are holes with threaded threads in there where you insert into there a tube. And those tubes go up directly into the cores. And the idea here for the thermal side of things is you can move that tube up and down in the core and position it so that the cooler air that would be here in the cell, as it gets circulated up into here, because the fans here are pulling air from the other side underneath the mirror into the cell. So that puts a slightly higher pressure in the cell than there is under the mirror. So that creates a circulation where this higher pressure air that's been conditioned by this fan unit wants to, just through the pressure change, go up through these pipes into the backside of the mirror. So as they're tuning this and trying to deal with the fact that, at the edge of the mirror, outside edge, you're this much of mirror, and then on the inside edge, you have a very, very teeny bit, you can move that tube inside and out to properly calibrate it to the right position it needs to cool that section of the mirror and at the same rate as it's being cooled in the rest of the mirror. That's a little inclinometer. Here is the very high-tech test electronics when we did not have the control system on a nice piece of wood. And there's our unpopulated bulkhead connector, where the cables would eventually be populated. Here's our temporary interlock system. As you can see, it's very high-tech, very clean and neat. And this was the first set of bending we did to the mirror. This one was with the surrogate mirror. So what you see here is the red color means you have the highest amount of force for the correction. And all the way this purple color here is the lowest amount of force. In this case, they're talking, it looks, I can't read it, that's probably like 74 newtons, and this is probably like negative 78 newtons. But what you're seeing here is the general shape that you're applying to the mirror, but represented in terms of force. So, there's a whole lot more pictures actually that anyone can go look at. And it's not just with the mirror system. You can look at the dome, you can look at the secondary mirror. They have pictures of it during various phases of the secondary and the mirror coated. You can look at a lot. You just go to gallery lsst.org and there's a lot there. So,
Well, the optical system, the light hits the primary mirror.
Yep.
Goes up to the secondary and down to the tertiary. Now, where is the camera located?
it's in the center of the secondary.
Okay.
So the
all
the secondary is this.
right. Like an
small-
angle,
yeah.
sort of.
Yep. And it goes through a bunch of corrector lenses, obviously the filter as well, and then into the camera assembly.
Okay.
But all that is attached to secondary. So even though the LSST is a 8.4 meter mirror, if you take out what is lost due to the size of the secondary obstruction, it's actually closer to the 6-point-something meter mirror in terms of light gathering area because of that very large obstruction.
But that's at 0.7 or something like that.
It's something insane, yeah.
It's not the same. Yeah.
Yeah, it's very, very fast. I mean, each image is a 15-second exposure, so over 15 seconds you're getting to like 26, 27 magnitude stars. It does not take long when you have that much light gathering area, which says a lot when you think about like TMT, when you have a 30-meter mirror, how fast that light is going to be captured. It doesn't, I can't even comprehend. So I also have a couple of, there was 2 videos that I wanted to show. So here is, what you're going to see next is this here is a video of the interferometry data as we go and bend the mirror, in this case for a trefoil. So we're going from a pallet to a trefoil here. This is just what the process looks like. The process of bending the mirror, we do it so that every single actuator, there's 156. You don't see the tertiary mirror here because you have to take that image data, that interferometry data at a different time. Yeah, we can't do both of them at the same time, technically. So all 156 actuators have to reach their new target at the same time, right? If some actuators have to change maybe only, let's say, 5 newtons, others have to change 50 newtons, right? The actuators that change 5 newtons are going to get there first compared to the 50 newtons ones. And that force offset, that unbalanced load, would then go to the hardpoints, which would then deform your image or reduce your image quality. Then they would eventually correct, and that would go away. But you would always then get this weird behavior of poor image quality while you're switching from one to the other. So what we had to do was make sure that as we bend it, everyone gets to their set point at the same exact time, so that you have a constantly balanced set of forces for your bending when you do that. And then what this same type of bend looks like on M3 is not as interesting, but like that. Right there. So
It's amazing the kind of control you have over that glass.
well, so with this, we have to raise it up, and it's about 7 to 8 millimeters that we raise it off of the static supports. And we use the interferometer to see how accurately we got to the same position. And we got there within a half a wave, so roughly 240 nanometers. So we positioned accurately to 240 nanometers, a 17-ton mirror. And we reference everything to the primary tertiary mirror because that is not accurate enough. So,
So you've written a lot of code for
I did the
controlling this?
whole system for this.
Yeah?
Yeah, for the primary tertiary mirror system.
Just you?
Yeah. So, let's see. We could show this. So here's the raw interferometry data during some of the bends. Oh wait, this is the long one. We're not going to do this one. Here, we'll show what it looks like from an interferometer's perspective of raising the mirror. So in this case, we actually did have both mirrors and the interferometers on at the same time. What you're seeing here is the structure of the interferometer to get M3 on the M1 mirror. So right now it's going through the process of raising the mirror, and it takes some time as it gets it up and gets it to the point where its reference position or the place it's supposed to go. And then right there, we are fully raised. If you know anything about interferometry, one way to think of it is the less lines, the better. If it's a perfectly flat image, then you've made the perfect optic. Or there's something wrong with your test setup, and you're tricking yourself. So I have this sped up because raising the mirror takes about 90 seconds, and it's really hard to see. So if you watch right here, you're going to start to see the static supports are raising up, and then a gap between the static support and this plate here. And so that's the mirror getting supported by all the support actuators and the hard points moving the mirror up such that they are, and there we go, we're fully raised. It's only a couple millimeters here, but those couple of millimeters make all the difference. And then when something goes horribly wrong, this is what our safe lower mechanism looks like. You'll hear a wonderful sound. And that's real time right there. So that's settling the mirror down onto the static supports. It takes out, to get to a safe zone, like 600 milliseconds to go from there to there. And it never exceeds, I think the requirement was 15 millimeters a second in terms of velocity. And then over here, I got a little graph. So on the mirror, we also have position sensors to tell us where the mirror is. And it's interesting to watch the raising on this. So this green line is where the mirror is in Z. Okay. And so as it raises here, what you can see is there's a slight change in slope. It's hard to see here, but right about here. And that's where the mirror comes off of the static supports. Because the static supports, while you're slowly incrementing the amount of force that you're using to raise the mirror, they are doing something. They're actually pushing still on the mirror. So that pushing though, they also do things like put little twists and turns into the mirror. They're putting moments and other things into the mirror. So all that is actually captured here by, you actually see from these sensors, the mirror is twisting a little bit. And when I say a little bit, I mean, it's a really small amount. But a little bit this way, it's not coming up like straight up. It might come up at a slight angle like this until, as it goes and does a little dance. And then once it reaches the reference point, you can see all of them over here come to basically 0, 0, 0, our origin position. So they snap in at that last moment. What else can we show? That we do have, we did an actuator run-in test for the dual axis actuators that made a nice sound. Which was, I found entertaining. As the pneumatics go. it was interesting. It's like, maybe we can make music with this.
So, trying to go to Game of Thrones.
So, and then this one is what a bending mode change looks like. There we go. So these don't make a loud sound. These would be very quiet. They need to be very stable and smooth. But I always just liked how it looks as it does that transition from one to another. Come on, play.
Why did you leave? Sounds like that's a fun project to work on.
I had a kid,
Oh,
and I
well,
decided that we wanted to be next to family. So
yeah, I guess you'd be down in Chile for a long time.
yeah.
Yeah.
And so I think that largely covers it. I mean, at a very high level. There's obviously a lot more going on behind the scenes than just that. But anyone have any questions?
Do you ever get calls to go back down for support, or do you do support over?
No, not yet, at least.
Isn't a lot of the software all custom? Specific?
Oh, all of this is custom. Each actuator has its own set of microcontroller code that's responsible for controlling that actuator. That we had outsourced to someone local in Tucson. I did the outer loop code that told each of those actuators what to do. I said, I want you to produce this much force, or I want you to move this many steps in this direction for the positioning, right? And then when you're talking about the observatory as a whole, you have the mount is manufactured in Spain. They did their own software. The dome in Italy, they did their own software. The camera is done in California. They did their own software. Data management side of things, that's largely out of University of Washington. They did their own software for that stuff. So there's not one software house. There's not one person providing the equipment. It is a very large and distributed set of people across many nationalities that actually do not just the software but the hardware, and I think it's representative of also the scientists and worldwide how the telescope is going to be used. Yes.
How do you make all the software from all these people work together?
Very difficult. It is not easy. It's very hard to go to even just locally a group and convey an image of how a telescope is going to work. Right? Someone has to have that vision, and then they have to be able to convey that image to other people so that everyone is on the same set of tracks, train tracks, and they're all working to that same vision and to reach that point. But then you take into something where you have a language difference, a cultural difference, and you're trying to convey that same type of vision. It gets hard. And so largely what it ends up being is you work and you do your best to do it beforehand, but it happens at the mountain. You get to the mountain, you start trying to make things work together, you find out this doesn't work, you go and fix it. You find out this doesn't work, you go and fix it. You find out your idea of how you wanted to make these two things interact with each other doesn't work, so you fix that, and you just slowly work through the issues as they crop up. It's by no means like the first time you plug it in and you say go, it works. It does not happen that way. That's why you don't see, in the news like, oh, new telescope X works on the day it was told to work. Right? That's why it's like 2 years later, 3 years later, 5 years later, 10 years later. Now we finally got it. It's because you have unique hardware, one-of-a-kind hardware for that telescope. You design it, you test it in a very nice place called a lab, where nothing can go wrong, but it does go wrong. But now you're going to take that same equipment and bring it up on a mountain where it's exposed to the elements. It's no longer this nice, pristine environment. And you're going to say, I want you to run for 10 years straight. and there's always going to be problems. You're always going to learn more about your custom equipment. Right? If anyone here owns a telescope, I'm sure they know that. You buy this nice new piece of equipment, you start using it, and then you figure out, I need to figure out how to use this. I need to really understand it to get the most out of it, and it's no different here. So,
Who owns it?
in the case of LSST, I don't know who owns it, but I can say who the primarily the NSF has funding it for the telescope portion. The camera is funded largely by the DOE.
US.
What's the current status of it?
It's still under construction in Chile. In July, the primary tertiary mirror made it to the mountain. The mount is not assembled yet, so they can't. They did some testing with the primary tertiary mirror and the mirror cell. That was back in October. But they can't put anything together yet until the mount gets fully assembled and starts getting tested there, and the dome gets fully assembled onto there. You don't want to put your mirror or even a surrogate onto a mount without some dome to enclose it and protect it.
Do you know what's the cost of the whole telescope estimate or not?
Ongoing.
I couldn't even begin to guess. From my perspective, I did not really care about the cost so long as I was getting paid to do my job.
So the assembly and testing you were doing, was that all in Arizona or was some of it in Chile?
It was all in Arizona that I did. The mirror cell was manufactured at a company called Cade. And that's where we did all our testing with the surrogate mirror. And then for the optical testing with the actual mirror, we did that at the Richard F. Karras Mirror Lab, also previously known as the Stewart Mirror Lab. We did all that stuff there where the actual glass was manufactured.
What are you doing now?
I'm a software engineer for aerospace defense company. So I still do software. I can't get enough of it. It is sometimes the most frustrating thing and then also the most exhilarating thing to do.
Any worries?
Yeah, finally get it to work.
Yeah, you just get like this adrenaline rush, like, yes, I did it. And then you find the next problem and then rinse and repeat.
Was no different in the amateur side, I could tell you.
Yeah.
Same thing.
It's not like a cell phone purchase where you have literally millions of units getting produced and tons of people telling you you're the manufacturer that something is wrong when something happens, right? You get these small firms, there's not a lot of people who buy amateur astronomy stuff. So you don't get the same level of investment in terms of quality, or it's not necessarily quality, but that finish, that finish like Apple gets out of their phone or Samsung, right? So it's more of that learning curve of figuring out and playing with it and gaining a deeper understanding of how you utilize it.
So you are.
You never just buy a camera, hook it up, and it works exactly the way you want it to. You still have to figure out, well, this camera has a different sensor than what I'm used to. What gains do I actually want to use? What offsets do I want to use? What is the best one for my imaging area? And then you gotta go play with it. You know, you might find something online, someone says, well, these are a good place to start, and those are always helpful, right? When you find something like that. But there's so many different variables involved, right? You're seeing at the site that you primarily observe at, your telescope, your optics, your filters, the software you use can play a role in it in terms of whether you're guiding or not. It's just, for me, one of the fun parts of the amateur astronomy is getting to that point of learning your hardware. Yeah.
Had you stayed there, would your role have diminished over time?
No, it only gets worse. You get more and more stuff When you're building large telescopes like this, it is very, very common that there is a large employee change between the design phase and when you get into the integration phase. The people who've been designing it for 9, 10 years straight, you know, they get to the point where it gets really hard to just continue pushing through. So you typically see a large number of people move on to something else. Maybe those people just intend to enjoy that design work more than the test work. So typically there's a huge portion of time where you start getting more and more responsibilities because there's just not the people there to do it. So for me, had I stayed, I was going to be involved with the active optics side of things. So the getting the active optics algorithm implemented into a software to take wavefront data from the camera, process it to a wavefront error, bring it through to a correction that gets distributed then to the primary tertiary mirror, the secondary mirror, to bend those mirrors to try to remove that error and get down to a really nice figure and image quality out of it. And then when you get to there, you have like software developed by other companies, and you're going to inevitably find that something doesn't work the way you want it, so then you have to go change all that software. It is also not uncommon when you receive a set of software, you start working with it, and you find it met the requirements that you provided them contractually, but when you tried to integrate it into your system, it didn't work the way you wanted it to. So then you rewrite the whole thing. So there's just always more to do when you're in the phase that the telescope is in right now. There's always more to investigate and to look at and to change. Scientists are notoriously difficult to please. They always want more and better out of their instrument. So there's always work to do if you're willing to move to Chile or move to where the telescope is. Where the telescope is where the work is. You won't necessarily, initially you'll be at the mountain very, very often, but once it gets into a more standard operations, you're not going to be there as often, only when they really need you there. But you would still need to be close by so that you can, and in the case of LSST, I think it's like an 1.5-hour drive just to get to the mountain, to the telescope from La Serena. That's the main town or a city that's close to the telescope site, and that's where FORA is the Association of Universities for Research in Astronomy. That's where they're based out of in Chile, Serena. So there's always more, never ending more.
Since you custom wrote a lot of the software yourself,
Yep.
and then left, how often do you get called?
I was called in October, but it ended up not being a software problem and more of like air hoses are not connected properly or actuators are not connected properly or things like that.
Mm-hmm.
So thus far, nothing software related, happily. That will maybe change. I don't know. You never know. Anything else?
Thank you very much.